time to start looking at samples and how it ties into normal distribution. And so what we're looking at here is when we take a sample and we want to find different probabilities of a sample occurring based on normal distribution. So a couple of things that we're going to look at here, and this is kind of all the different components of Chapter 7, and I'm going to hit on some briefly here, and that's looking at a point estimation and understanding really what a point estimation is and what a sampling distribution is as well. And then we'll look at the different ones for a value of x and also for p. And when we say p, we're talking about a proportion. So, you know, we know that the let's say the approval rating for the current president is at 48%, and we take a sample of 50 individuals and we find out it's 30% here in Middle Tennessee. Well, what does that mean in terms? There's a difference between the sample proportion and the population proportion in that case, and you want to look at things in those cases. So that's kind of what we're going to look at with this. In every case, when we look at a sample, we'll look at the sample up here in a second, you're comparing a sample to what you think the population is. And so when we do that, there's a couple of things that you can really think about. So here's some data. It's looking at SAT scores. And what you see there under parameter value is all of the population data. And what we have there is a population mean SAT score with the population standard deviation. And then you also have a proportion of students wanting campus housing. And so for the population, which means everybody that took the SAT, they were asked that one question, and 72% seemed to want campus housing. And then what you see on the other side there, the point estimate, is what you get from a sample of 30 students. And so looking at those 30 students, the average is a little bit different, the standard deviation is a little bit different, as well as the proportion. So looking at this data, let's take a look at finding some different probabilities. So the expected value in this case that we would have expected of our sample is obviously the population mean if there's no bias in any of our data. Okay, so then lastly, just looking at this, one thing we can kind of say about sampling distributions is, and this should make sense, the larger the sample, the more accurate it is. And that should hopefully make some sense. And then it also tells you that the larger the sample, at least 30 usually, the more of a bell curve your data will look like. So if you think about it, you take a sample of 5, it could be very skewed one way or the other. If you take a sample of 30, well, you'd expect it to be pretty good. And if you took a sample of, let's say, 1,000, obviously you'd expect that to be a pretty good representation of the population. Just to give you some examples, I know that when they do approval ratings for TV and stuff like that, you need at least 1,000 individuals to have a plus or minus of 1%. So that kind of gives you an idea. And actually, that's what we do in Chapter 8, is how to figure out that percentage. Okay, so let's take a look at this and the example. So we've got 30 individuals, and we want to provide an estimate to find out the probability of somebody being plus or minus 10 points to the population mean. And so we're going to look at that in those types of terms. So what we have up here, though, is let's say we did have a sample and we found out that's what our sample really falls into. Well, that's fine, but what we want to know is if we took a sample of 30, what is the probability that it's within plus or minus 10? And then we can also see that our sample that we have up there is actually different. So let me ask you this question. If I just want to know the probability of one individual scoring 1,687 or less, what is the probability of that occurring? And what would you do? Well, you would take your Z-score, calculate a Z-score as you see up here, and then you would with that z-score, you'd find the corresponding probability. This is chapter 6 stuff. And then with that corresponding probability, we could tell you where we are. Well, now I'm not saying that, okay? I'm not saying a value of x. I'm not saying one individual. I'm saying a sample of 30. If I took all 30 scores, what's the probability of being between 1687 and 1697? Or less than 1687? So how do I find that information? Well, don't you think that a sample would be more accurate than one individual? One individual can go pretty far from the mean, but a sample of 30 does not move as much. So being out here would probably be, maybe not for one individual a big deal, but for a class, that might be a big deal. So that's what we mean when we're talking about sample versus a value of x. So here's the big difference. You ready? This is the whole big difference in this chapter. It's a real big difference. Okay, we're not doing a value of x, are we? We're doing sample mean. Okay, that's a big difference. I'm sorry, I had to draw a line there for you. The other thing is, instead of dividing just by standard deviation, we are going to divide by the standard deviation divided by the square root of n. Okay, so the square root of n, when you look at this here, is something called standard error. And so that instead of standard deviation, you're dividing by standard error. And if you know that, then it makes everything else is the same. You still come up with a z-score. You still come up with a probability that corresponds to that z-score. And you still add and subtract it from 0.5 or from 1.0 to come up with your answer. And so we can do that, right? We can do that for this particular problem. So let's take a look at that. So with this example now, what we are going to look at is the 1707 value first, the upper point, and we've got that here as on our bell curve. And with that, we take that value minus the population mean. So let's take a look at that here. Let's get red. There we go. So there's the 1707. Subtract it from the population mean. And then we divide it by that standard error. That standard error is what you see over on the side. And that gives you a z-score of 0.63. Well, if I look up 0.63 in my table, I will find a probability of 0.7357. So if I look at that here, you can see there's 0.6, there's the 3, and that's 0.7357. So what does that mean? That means from negative infinity to a value of 1707. Let's take a look at that up here. I draw it this way. That will be our 0.7357. Just get rid of this here. And the z-score at this point is 0.63. So hopefully you also noticed that a z-score on the other side would be the mirror image if it's exactly 10 away from that. But you'll see what I mean here in a second. So anyways, there's what our bell curve should look like. And then if we now do it for the lower one, it's going to be the exact same value except negative. And when you look up a negative, you're going to get the same thing pretty much just on the left side. And you see here, that's actually the complement of our other value here. Let's see what we get. And that's actually the 0.2643. And so that means in this area here is that 0.2643. So then what math do we need to do to come up with the probability of being between 1687 and 1707? It's very easy. So what does that mean for what we have? Then if we look at this, we're going to take what we got for 1707, that probability, and subtract away what we have for the other one, which was 1687, and we are left with 0.4714. So the probability between 1687 and 1707 then is 0.4714. So looking at that, here you can see that shaded area in the middle is what we're looking for. So what are we saying here? Well, at St. Andrews College, based on a sample of 30, the probability of that sample of 30 being plus or minus 10 points from the population mean is 47%. That means basically there's a 53% chance that it could be less than 1687 or more than 1707. And if we look at that, actually let's take a look at that on the whiteboard here. What we're saying then, if this area is the 4714, this area then will also be close to that. Obviously for rounding it's probably a little bit off, but it's pretty close to that as our different values. So being the probability of being greater than 1707 is going to be 26.43. Between the two is going to be that 47.14, and then less than that is the 2643. So what's the real big difference here? Again, it's nothing more than using standard error instead of just the standard deviation. And then secondly, you're using the sample mean instead of just a value of x. So it's when you want to look at an entire sample and compare it to the population mean. Okay. Lastly, we want to look at an actual probability. And then finally, I just want to make the point of the difference in sample sizes. So a sample of 30 is one distribution, where if I was to take and have look for the exact same thing, except I had a sample size of 100, as you see up here, you can see the standard error value changes compared to the sample mean or the sample size of 30. And so what that means is your bell curve will be tighter to the population mean. So it's not as likely that a sample of 100 is way out here, but for a sample of 30, there is a chance it could be that far away. Okay? So the larger the sample size, the less likely it is to be far away from the mean. Okay, so if I did the exact same calculation using a sample size of 100, the probability of being between 1687 and 1707 is actually 77%. So you'd expect close to 80% of all the values to be between plus or minus 10, where if it was a sample size of 30, it would only be 47%. Okay, and that's what it would look like in that case. Okay, now let's take a look at a sample proportion. And so what we had talked about before Now let's take a look at a sample proportion. And when we look at a sample proportion, compare it to a population proportion, we can also do the same thing. We can still come up with a z-score. It's just the calculation's a little bit different. So if we recall from that first slide we saw way back when, 72% of prospective students, according to the population, which means all students at St. Andrews, desired on-campus housing. So they took a random sample of 30, and they want to know how it can be plus or minus 5% of that. So basically what we're talking about is what's the probability that's between 67 and 77%. So if I were to take a look at that, there's a couple things I have to do. First of all, I have to see if this is a large enough sample to use this with. And so we have a little formula there. So we take the sample size times the proportion, and then we take the sample size times the complement of the proportion. So that's what you see right here. Make sure you see this in the ebook and make sure you read further on this, but it's pretty easy stuff. If these two values, once you calculate them, are above 5, then it's feasible to use a sample proportions and z-scores. If not, it's not feasible. So, but in this case, we do have that, so we can do this calculation. So we put the 72% there. We are then going to look at the one side will be 0.67, the other side will be 0.77 on our bell curve, and then we still have to calculate a standard, a proportion standard deviation or standard error. And so the way that we do that is we take the population proportion, we multiply it by its complement, we divide by 30, and then the whole thing we take the square root of, and we should get that 0.082. So let me show you the calculation, because I think that's a little bit hard to decipher there. But this is what it should look like. It should be 0.72 times 1 minus 0.72. You divide that by 30, and then you take the square root of the whole thing. So hopefully that makes a little bit more sense than what you see up there. And then that value should be that 0.082. And so that's what we use as our standard error for a population proportion. So doing the math to find the higher one, it's 0.77 minus 0.72 divided by 0.082. Let's take a look at that here. So if I put 0.77 here, 0.67, I'm taking my sample proportion and minus my population proportion over the standard error for the proportion, which actually I'll denote it as that. So I get my standard deviation, and then okay, let's take a look at another example. In this one, we're looking at proportions. And so if we have proportions, if we meet certain criteria, which I'll show you on the next slide here, then we can use proportion data with z-scores to come up with these probabilities. So if we find out that at St. Andrews College, 72% of all students want on-campus housing, if we want to know the probability of a sample of 30. So if let's say we have 30 incoming freshmen, and those individuals, we know the probability of the proportion of those students being between 67% and 77%. What's the probability of that occurring? We can calculate using z-scores. But the way we have to first figure that out is, do we meet the criteria to use z-scores? And these two formulas must be more than 5. So the population proportion is 0.72 times the sample size that is larger, and then 0.28 times 30 gives us 1, and it's still larger. So this is just a checkpoint to make sure that we do have a large enough sample to use proportions and z-scores together. So now what we have to do, if you think about it, we've always had to take a sample something minus a population divided by standard error. So how do you calculate standard error? Standard error is a pretty easy formula. Now I'm going to show you it up here because I think it'll be a little bit easier. But you're going to take the population, draw a nice one here, population proportion times the complement of the population proportion, divide that by 30, and then take the square root of that, and you get that 0.082. So that's where that 0.082 comes from. That then becomes the denominator of our z-score calculation. And when we do that, we end up taking 0.77 minus 0.72 and then divide by standard error, and that's what gets us at 0.61. So the z-score at this point is 0.61. Okay, what do we do with that 0.61? We look at our table, we go down to 0.6, over to 0.01, and we get a probability of 7291. As you see up there. And that's where you can find that probability. Do the same thing for the 0.67. And of course, you're going to get the same z-score, just going to be negative. And the probability that corresponds to that is 0.2709. And as you see, that's what it should look like up there. I'll leave that there. So that, again, was 0.709. Which means to find this area, I'm going to take 0.7291 minus 0.2709. And on the next slide there, it'll tell us what that answer is. There we go. So 0.7291 minus the 2709 gets us 45.82%. So there's a 45.82% chance that the proportion of students out of the 30 that want campus housing that it's between 67 and 77% is that 45.82%. So that's how you do a population proportion and compare it to a sample proportion to come up with a value. You can, for any, now I'm showing you just for one on each side. If I just want to know the probability of it being more than 77%, then all I'm going to do is take 1 minus 7291, and that gives me my correct answer, and so on. So I don't have to do this for two different values, one on each side. All I'm doing is finding a z-score, finding the probability that goes with that. The difference being, instead of standard deviation, we're using standard error, and it's either a sample proportion compared to a population proportion, or it's a sample mean compared to a population mean. And that's all we're really trying to focus on for Chapter 7.